So today I will talk about discovering and characterizing inorganic materials, and this will be done with the standard techniques, the density functional theory, that is the standard technique in material science, in theoretical material science, combined with machine learning. Our perspective is from a big data point of view, so you will see, we'll talk about millions of calculations and large machine learning models. And in this context, we will just use machine learning to accelerate density functional theory in some sense. We are not going to replace density functional theory or density functional perturbation theory at this level. We are just going to use it as an accelerator so that we can do things perhaps 1,000,000 times faster than before. But in the end of the day, our results, the results I will present, are good old results done with density functional theory without the added machine learning part. So the machine learning will appear in the workflows, but in the end, we will always resort to our good old techniques. So this is the outline of my talk. I will discuss, to start, the problem of materials discovery, what we mean by discovering materials in a computer, what quantities we have to look at. And then I will briefly go into the problem that we have, the combinatorial problem that underlies physics and chemistry. And I will give you our solution or partial solution to this problem using machine learning to accelerate this discovery of materials. Then we will go to the results that we already have. This is the main part of the talk. Then I will, if I have time, go through the application of the same kind of techniques for 2D materials. And at the end, how we can increase the accuracy of all this workflow, and how can we make more accurate predictions that are more in line with experimental results. So let us start. So our major objective is to discover new inorganic materials. I will just talk here in this talk of stoichiometric compounds, crystalline compounds, ordered compounds, and only inorganic materials, not organic compounds, okay? I'm not saying that these compounds are not important, but we have to restrict ourselves in some sense. So this talk only inorganic ordered stoichiometric compounds. So our general objective is to find all possible inorganic compounds that are thermodynamically and dynamically stable. So what does this mean? Thermodynamically stable means that these compounds will not decompose even in an infinite time into other compounds. That's the meaning of thermodynamically stable. Dynamically stable means that the crystal structure makes sense, right? That it will not distort or change in any way. We will do it by doing what is called by many people prototype search. So by grabbing structure types that are known, and by changing the chemical elements in the structure types. So this is the first step. We'll try to find all possible inorganic compounds. There are much less than people believe, at least in this set of inorganic stoichiometric compounds. And then, only then, we will scan the compounds for interesting properties, extreme properties, we may call. So values of properties that are in details of the distributions. I will discuss it in the following, because these are materials that might be interesting for some technological application. The rationale for this strategy is the following. So it is true that the number of possible crystal structures grows factorially with the number of chemical elements, with the size of the unit cell, and so on and so forth. But the truth is that the number of stable compounds, thermodynamically and dynamically stable compounds, is relatively small. So if you look at the inorganic crystal database, it only has around 50,000 materials. So there are more entries, there are more than 200,000 entries, but the number of different inorganic materials in this database is not much larger than 50,000. 50,000 is a very small number when compared to the infinite number of possibilities. The major problem is thermodynamics that constrains a lot what crystal structures can actually exist, which materials can actually exist. So, of course, 50,000 is a lower bound. Likely the number is a couple of orders of magnitude larger, but it's still not exceedingly large. So it may be of the hundreds of thousands, million, 2 million, but it's not exceedingly large. There are still numbers we can handle. So this is the first reason. So we have a chance, we have the hope of finding most structures that may be stable. And then by knowing all these materials and by plotting distributions of materials properties, we can define what extreme means. What does it mean to have a large band gap or a small band gap? What do these adjectives actually mean in practice? And we can estimate probabilities. So we will be able to say we can find a material that has say band gap between 3 and 4 electron volts will be 1% or 2 or 3. So we can only know these probabilities if we know the distributions. And we only know the distributions if we study a large selection of materials. So our basic assumption also is that current theories, that means density functional theory with some standard exchange correlation functionals, are good enough for most material properties, for most materials and for most properties. Of course, there will be exceptions. There are materials that are very badly described. There are properties that are badly described. We know that. But statistically speaking, the theories are rather good and they are predictive. Of course, our predictions will always be interpreted statistically in the sense that if we propose materials for a certain application, our basic point is that we propose 10, hoping that a few work. Okay, this is much better anyway than just randomly trying out materials. What do I mean by thermodynamic stability? This, I think, is already well known, but I think it's a good thing to insist on this point. So, thermodynamically stable materials, they are materials that are, mathematically speaking, that define what we call the convex hull of thermodynamic stability. This is a hypersurface in what we call chemical space. So it's a space that is defined in each axis by a chemical element. So it's around 100, it has around 100 dimensions because we have around 100 chemical elements. And to visualize this hull, this hypersurface, is very hard because the space is very large. So to give you an example here, I just plot a two-dimensional convex hull or a two-dimensional phase diagram where I have some fractions. So this is a binary phase diagram. So I have A on the left and the compound B on the right. And in the middle, in between, I can make any binary compound by mixing A or B. Now, a compound will form, so a compound will be stable, this is what I mean, if it cannot decompose into any other compounds. What does this mean? Imagine that I have a certain compound that is represented by this blue square, and I calculate its formation energy, and I plot it in this diagram, and the formation energy is here, so it's this red, this blue square. If I compare this energy of this compound, this fictitious compound, with a mixture of A and AP2, we see that the energy is larger than the linear combination of these two compounds, A and AB2. This means that thermodynamically, in an infinite time, this compound, this blue square, should decompose into A and AB2 because the energy of the decomposition is lower. On the other hand, if I have another compound, for example, an A4B here, this green square, the energy is lower than the linear combination between A and AB2. This means that this compound cannot decompose into any channel, so it is stable. Now, the convex hull will be this dashed line here, then continuing, and it is the line that connects or the surface that connects all compounds that are thermodynamically stable, that cannot decompose. The distance in energy from a certain compound to the convex hull gives us an idea of how stable, how metastable, this is the correct term, a compound is. So if compounds are close to the convex hull, I can have a hope to synthesize it. If it's on the hull, it should be relatively simple to synthesize. If it's close, I do have some hope. If it's very far away from the hull, it is impossible physically to decompose it, to synthesize it. In fact, the probability to synthesize a material decreases very rapidly with the distance to the convex hull. And if this is beyond a couple of 100 milli-electron volts per atom, then it's very unlikely that this material can be synthesized. There are of course, our energies are calculated with density functional theory, normally with PBE. There are other possibilities. They have an error that we also have to take into account. But keep in mind that if we are more than a couple of 100 milli-electron volts per atom above the hull, it's almost impossible to synthesize the compound. If it's on the hull or closer, this probability is much, much larger. So we will concentrate on materials close to the hull, obviously, so that they are relevant. Now, to find new compounds, there are two common possibilities. The first of them is, so there are two paradigms, let's say, and everything in between. But the two paradigms, in my view, they are the first one, you keep the stoichiometry fixed. So you keep the composition fixed. So you have 3 carbons for 5 hydrogens and 8 coppers. And then you search for the minimum energy, for the structure, the crystal structure with the minimum energy. This can be done using what's called global structural prediction methods. There are many of them by now. They are very successful in some fields. For example, the high TC superconductors that were found at very high pressures. They were all, or in most cases, found theoretically using these methods and only then experimentally produced. They are very thorough and unbiased, but they're computationally very expensive. So using these methods, at the moment, we cannot explore the whole chemical space. The other approach is that we keep the structure, the crystal structure fixed, and we will search for stable compositions, stable chemical compositions. This is known as prototype search. It's also known as component prediction. This is relatively fast. This means for every crystal structure and chemical composition, we just have to do a geometry optimization with density functional theory and then check the energy. The problem here is that we have to know the crystal structure. We have to know the prototype. Now, this approach of prototype search leads to what we can call a combinatorial curse. Let me give you an example for this to be clear. Let us take as an example ternary intermetallic compounds. This means ternary with 3 chemical elements. Intermetallic, this means these elements are just metallic elements. We have around 60 of these in the periodic table. Experimentally, we know that there are around 1,400 different structure types in which these ternary intermetallics crystallize. So these are the ones that are experimentally known. The average number of atoms in the unit cell in this 1,400 structures is around 14. Now, if I do the number of different combinations for ternary intermetallic compounds, I get this nice number, 3 times 10 to the 8. These are the number of intermetallic compounds I would have to study if I wanted to study these 1,400 crystal structures. This number is obviously very large, and we cannot do 3 times 10 to the 8 density functional theory calculations. We cannot. Moreover, we have to keep in mind that most, really the large majority of these combinations are highly unstable and are not relevant for mankind because they will never be realized in a lab because they're just too unstable. So our problem is to find out which combinations are stable or close to stable. Remember, this example I gave is just ternary intermetallic compounds. You have to take into account there are more chemical elements in the periodic table, and there are also many compounds that also have these non-metallic elements, so the true number of combinations is much, much larger than this one, okay? So this is, in principle, hopeless if you just do density functional theory. So how can we solve this problem? Well, we can accelerate calculations. The basic idea still holds. We can do systematic brute force searches, but they have to be faster. And to be faster, we will use machine learning. Machine learning studies in this kind of context, they all follow more or less the same workflow. In our case, we built a materials database of density functional theory calculations. I will talk about this shortly. We use them to train a neural network. Again, I will give you more details later. This neural network will just try to reproduce the density functional theory results. The advantage is that it's much faster. So we can emulate the density functional theory calculation maybe 1,000,000 times faster than if we had to do it. Then, as this machine is very fast, we can use it in a completely systematic way and generate all possible crystal structures in a combinatorial way, use it to predict the energy. Then we will filter based on the energy, so we will just take a look at the compounds that seem to be stable or close to stable. This we select, and then we validate them with density functional theory. Then we will filter them out again according to some property. We will go back to that also later. And then the ones we find interesting in some respect, we propose them for synthesis or further studies. So that's the basic idea. That's not very complicated. The devil is in the details, like we say, and let's look at a little bit more into the details. First of them, the data set. To do this kind of general study, we need a lot of data. There is some data already, or a lot of data available in the community. We have to be a little bit careful because this data should be consistent in some sense, and that's maybe the greatest difficulty that we have. So at this point, and this was already 2 or 3 years ago, what we did was collect the data from sources that were more or less compatible. So we used Dayflow, Materials Project, and we also have quite a lot of data already in our own group. This has changed by now. By now, we don't longer use Dayflow and only a very small part of the Materials Project, but this was the situation 3 years ago. We curated this data. This means we filter, try to remove duplicates, got data only with compatible parameters, and so on and so forth. And in the end, we had a data set of around 2.4 million entries. That is summarized here. So this is the distance to the convex hull of the different parts of the data set. The message here is that the distance, by looking at this diagram, is that you see the distance to the convex hull goes from 0 to about 4 eV. We are interested really in this region very, very close to 0. So again, we are looking at the needles in a haystack, in a very big haystack. So we have our data set. These are, I recall, I repeat, there are around 2.4 million density functional theory calculations for some crystal structures. Then we have to represent these structures somehow for the machine. The state of the art now is using graphs. So one represents these crystal structures in graphs where the nodes of the graphs are the atoms themselves. The links between the graphs, so the edges, are related to bonds, if you wish, or neighbors. We had to change a little bit the standard representation, graph representation of the crystal structures, because in order to build this representation, you usually have to know the crystal structure. And we do not have the crystal structure for compounds that we haven't calculated yet. So we had to make the representation a bit more abstract. And in our machine learning approach, we do not use absolute distances. We only use information about the neighbors, how many they are, and what kind they are. But it's very similar to what is done nowadays, just a little bit changed, as I told you, to not to use the precise information about the structure in the graph, just information about neighbors. This representation is then changed by a series of, let's call them convolutional layers. They use message passing and they use attention heads. So there are concepts that came from natural language processing. This will allow the network to change this representation into something that is more suitable to predict material properties. So the graph is then transformed into a vector by a pooling layer, and this vector is then used as input. You can call it a feature vector by now, is then used as input for a fully connected network. We call that a residual network. That will be the network that will predict the property we are interested in. So the most interesting property from our point of view is the energy that will give us access to thermodynamic stability. Of course, we can use this to predict any other material property that we have, and we also have used it for other material properties. But in this talk, I will actually concentrate on the energy. For you to have an idea, our network has 62 million parameters. This is rather large for the materials science community, but it's still rather small when you think about big models like the large natural language models. For example, GPT-3 has 175 billion parameters. GPT-4 is not known, but one expects it to have considerably more, at least 1 or 2 orders of magnitude more parameters than GPT-3. So we are still way smaller than these large models. But as you will see, this is, for the data we have and the problems we have, this is already quite sufficient. So having this network, we have the network, we can use it to predict, as I told you, stability of crystal structures. Then we filter them, we select them, and we perform density functional theory calculations of the most promising ones. So this is the result of this search. We searched all binary, ternary, and quaternary prototypes we have in our database. There are quite a lot of prototypes, and we had to put some cutoffs to make this possible. So we just looked at unit cells with a maximum of 20 atoms. These are already relatively large unit cells. And we kept some symmetry. We just chose unit cells that had a space group number larger or equal than 10 in order to make the calculations a little bit more efficient, because the monoclinic space group doesn't have symmetries, makes things a little bit slower. These choices are just totally arbitrary. They're just related to our available computational resources, and we have, in fact, already gone beyond these limitations more recently. So we looked at material space. So the ternary space was of around 1 billion compounds. The quaternary space was around 13 billion compounds, so 14 billion compounds in total. And by doing this and performing this density functional theory calculations, we found 43,000 new compounds on the convex hull. I will put this in perspective just in a minute. We also have by now around 500,000 compounds that are within a small shell of 50 millielectron volts per atom of the convex hull. The histogram is on the left. As you see, if you remember the histogram I showed you just in a couple of slides before, I told you these histograms went to 4 electron volts. This one, it basically goes to 0.6 electron volts, which means that the machine actually was very successful in choosing already compounds that were very close to stability, with a certain error, of course. Our current database, and these are numbers from a few months ago, we have 4 million compounds now. Most of this database is already public. You can download it in the materials cloud. We are working on putting it in Nomad also. And our whole, again, these are numbers from around half a year ago, we have now around 105,000 materials on the whole. For you to have a comparison, our whole before crystal graph networks was composed of around 49,000 compounds. This is again already considerably larger than, for example, the whole of the materials project that is around a bit more than 30,000 compounds. And in essentially 1 year of calculations, we were able to extend that, almost double it, with another 43,000 compounds. The message here is that there are many more materials, even in the ternary sector, that are there to be discovered. And each one of these materials can have properties, extreme properties, and be useful for technological applications. Now, I don't know what is the limit. I don't know how many compounds will be in the convex hull. I believe very likely between 500,000 and 1 million. We will certainly, this number will increase very rapidly in the next months of years, because the whole procedure is kind of self-correcting and self-accelerating. Because the more data we have, the better we can train our neural networks, our machine learning models. The more accurate the models become, the faster the high throughput part will go, because the less materials I have to take into account, and so on and so forth. So this whole procedure, like very often in machine learning, is self-correcting and self-accelerating. So this number will certainly grow up very, very much. Let's just see what we have. Yeah. Now, why do I want all this data? And that's maybe the most important question, right? So I told you that I want to print histograms of materials properties to start. And for you to see what I mean, I just put here a very simple example. And this is the histogram of the stable materials, or close to stable materials, that we have, of the volumetric mass density. So how dense a compound is. And let's look at what, so first of all, and this is something that was very surprising to me, and I suppose for many people, is that distributions of material properties are all, at least all the ones we plotted up to now, rather complicated. They are not Gaussians. We haven't found a single Gaussian in all these properties that we have plotted. So you see, clearly this is not a Gaussian distribution. It seems to be bimodal. I honestly don't understand why, but it's certainly bimodal. And it has a relatively fat tail. It is not an exponentially decaying tail. It's a fat tail that goes up to around 20 grams per cubic centimeter. What are the extreme materials? That's the other question. So first the conclusion, these material property distributions are complicated. They are smooth also. So there are no unicorns. There are no exceptional unique compounds. So we just see that the distributions are all very smooth. Extreme materials are materials that are at the tails of the distribution. So in this case, which are the extreme materials? Well, at high density, plutonium is the most dense material. Lead, of course, lead is not particularly dense in comparison to many other things. Plutonium is not a very interesting compound, as you know. If we remove all these radioactive elements, the highest density compound is a compound of iridium and osmium that I have the picture here. It's iridium osmium 3, and other iridium osmium compounds. Some of you probably know that osmium is the densest elementary substance, so this is not perhaps a surprise. Now, what is the other extreme? This is also very interesting. The other extreme, the low density extreme, and of course excluding gases, because those are not really interesting in this context, the lowest density compound is magnesium borohydride. And again, this is a material that is known and that has been studied a lot in the context of hydrogen storage. So there are several polytypes, there are several structures of magnesium boron hydride. This is the one in our database that has the lowest density. Okay, so this is the kind of things that we want to do: plot materials distribution, distribution of materials properties, and look at extreme cases. So this was a rather straightforward, very simple property to calculate and to plot. Let's go to a non-trivial property, very non-trivial property, and let's look at conventional superconductivity. Okay, so we will just look at conventional superconductivity because it's something we can calculate, and it's our theories work rather well. So we have filters from our database metals. We calculated a lot of them. We trained machine learning models to predict them, and we have been doing this for almost 1 year now. And these are some histograms that we already have. There are around 8,000 compounds that are in these histograms. So we performed 8,000 electron phonon calculations with density functional perturbation theory. And these are the results. So the first thing that was really surprising, and again, maybe it's no longer surprising, is that if we make distributions of the electron phonon coupling constant lambda, or this logarithmic average frequency omega log, we find out that they're, number one, they're smooth. They appear to be very smooth, and that they follow log normal distributions. Now, clearly the distribution has to be asymmetric because these quantities are positive, are strictly positive, so they cannot follow symmetric distributions, right? But why it's a log normal distribution, it's a big mystery to me. The tails are hard, so the tails are very important because they are where extreme materials will be. In this case, materials with the highest transition temperature will come from the tails of the distributions of lambda and omega log. Here, it's very hard to say what kind of tail there is because of statistics. There is certainly a fat tail. It's not exponential. Now we cannot say if it's polynomial or not because we don't have enough data for that, but the tail is fat. This fat tail, if we assume that it's actually the tail from a log normal distribution, should actually lead to materials with very high TC. TC is probably exceeding 100 Kelvin. The problem is that materials with large lambda, we know, have often dynamical instabilities, and this cuts off the tail of TC. And so you see that if we plot the distribution of the conventional transition temperature, we get something that decays exponentially. There are some materials that seem to be beyond this distribution. Our current record is around 100 Kelvin, but there are very, very few. Very, very few, and they're really exceptions simply because we are in the law of small numbers, right? And you see that we are in the order of numbers of the order of 1. So in order to be able to find them and to have a smooth distribution, we will have to have millions of compounds. Anyway, so I want to show you one example. This is from the materials that are known experimentally. This is the most interesting superconductor that we found. This is a material that was synthesized already 30 years ago, and due to theorists saying that the material did not look interesting, it seems that it was completely overlooked in the search for superconductivity. It's lithium molybdenum nitride. This is a layered compound with layers of molybdenum nitride intercalated with lithium. But although the material structurally is two-dimensional, the Fermi surface has also three-dimensional components. So the Fermi surface is pictured here. And you can see in the center, there is actually a part of the Fermi surface that is three-dimensional, while there are still some parts that are two-dimensional. And this is what led theorists 20 years ago saying that this material was not interesting for superconductivity because the opinion at that time was that you required absolutely two-dimensional Fermi surface in order to get a good superconductor. Well, we performed the electron phonon calculation. We used Eli-Ashberg theory. We used density functional theory for superconductors. And our lowest estimate for the transition temperature is 40 Kelvin, which, if it's confirmed, would actually be a record for conventional superconductivity. Now, this is again in the computer. This material, of course, is at the edge of every kind of instability that you can imagine. You already can see in the phonon spectrum that is plotted here. There is a soft mode that in our calculations is real, but it indicates instability, very likely a charge density wave instability. So we're very close to charge density wave instability. Experimentally, they also report there is some alloying going on. So all these things would decrease the transition temperature. So the thing we can state is that if this material can be done, the closer you get to stoichiometry, the higher TC will be up to a limit of very likely 40 Kelvin or above. For curiosity, this same compound in the chalcopyrite structure, it's slightly unstable thermodynamically. It's 15 milli-electron volts above the hole, but it already has a transition temperature of 20 Kelvin. So this is from the compounds that are non-experimental, as I told you, the most interesting we found. We also use this data to study whole families of compounds. I here give you the example of garnets, that are compounds that are used technologically in a series of things like for lasing and things like those. We studied the whole family, and as it's common nowadays, we find a lot of systems that are on the whole or very close to that are not known experimentally. The most obvious in this case is the sulfide garnet. So experimentally, no sulfide garnet has been synthesized up to now, to my knowledge. But we do predict a few of them. We also predict selenites, tellurides, and even nitride garnets are in principle possible. I'm not saying that they are easy to synthesize. I'm just saying that from our calculations, there are many of these systems with very interesting, some of them, very interesting electronic properties that should be synthesizable. This is true for essentially every other compound family that exists. Now, let's move on to two-dimensional compounds. How about them? Can we do the same thing for two-dimensional compounds? Well, the truth is that we couldn't. And it all boils down to training data. There is very few training data comparatively for two-dimensional materials, and more than that, there are very few structural prototypes known, very, very few. So without data, we cannot do machine learning. Actually, one can even say that data is more important than the neural networks. So data is certainly the most important thing. So we had to go around this, and in order to get data, both to train our networks and second, to obtain prototypes, we did a systematic search using a workflow that is based on space groups and Vy'kov positions. So at the moment when we submitted this paper, we had studied 23 different Vy'kov space groups, binaries and 4 ternary space groups. Now we have them considerably more. And we generate in this way, in a systematic way, crystal structures that we optimize with density functional theory. And we use this as a starting point then for machine learning. Now we have a series of problems. This is, of course, not very efficient at all. One of the problems that the systematic approach leads to structures that are often very far from dynamical equilibrium, and so it's very hard to do geometry optimizations. We again solve this problem with the neural networks. We used a universal neural network force field. That means a force field that is trained on DFT data and tries to reproduce this data, so the potential energy surface, but for all chemical species. That's where the word universal comes from. And in particular, we retrained a force field, a magnet force field. The stock force field is for 3-dimensional compounds, and it's rather good. We retrained it with our data in 2-dimensional systems, and this actually made the whole procedure much more efficient. Just for you to have an idea of the structural variety that we have, so now we have a very large database of stable or close to stable 2-dimensional systems. We have found essentially every single paving or every single tiling that you can imagine. I have a few examples here, from normal square lattices, hexagonal lattices, to more complicated square snub lattices, or even Kagome lattices. Everything, essentially every lattice that exists, we found examples of them. And some of these materials have very interesting properties, of course, very different from what one knows, because the structural diversity leads to diversity of properties. Everything is based ultimately in the structure, of course, as you know. This is a summary of what we got. So this is again a histogram of the distance to the convex hull, and you see the systematic search leads to compounds that are sometimes rather unstable. This is then becomes much better when one does machine learning and all our prototype search. But as I told you, in this case, we were rather limited because of the inexistence of training data. In any case, we now have around 100,000 compounds calculated, and so our machines, as I told you, it's all self-accelerating. So our machines, both the prototype, the one for the prototype search, as the universal force field, are now rather accurate, and so everything is accelerated a lot in the last months. So we can expect to have many more compounds close to the hole in the near future. Now, just to finish, a couple of words about accuracy. All these things I showed you were done with the Purdue Berke-Herzenhof functional. That is the workhorse functional in material science. Of course, there are some imitations. We all know them. And we would like to go beyond. And to go beyond, we made a large computational effort in performing PB-Sol calculations, PB-Sol geometry optimizations, because the PB-Sol geometries are considerably better than the PBU ones, and performing PB-Sol and scan energy calculations at this equilibrium structure. We have by now a data set that is public of PB-Sol and scan of around 450,000 compounds, out of which 235,000 are close to the hull. I don't know if you can see it. It's this green curve here. So you see it's all very close to the hull. And we use this data to do transfer learning. So transfer learning means use the information that we already have from the 4 million PB calculations and just retrain our models that already know chemistry and physics, because PB already knows a lot of chemistry and physics. So transfer them to other functionals like PB-Sol or scan. And we know, not only from this work, but from many other in the literature, that transfer learning is a very efficient way of doing things. And what we concluded is that just 10,000 scan calculations were actually enough to reduce the error of the machine that predicts scan energies to 33 millielectron volts per atom. Now, 33 millielectron volts per atom is chemical accuracy. It's beneath the 1 kilocalorie per mole. And this can be achieved by 10,000 calculations, which is nothing. Yeah, it's really nothing. So the most difficult part is actually to obtain the convex hull in scan. It's not to do any further calculations. So this is very promising, and very likely using transfer learning approaches, strategies, we'll be able to have much more accurate calculations, machines, and results that are in much better agreement with experiment, with a relatively modest computational effort. So doing this, we can even think about doing hybrid calculations. 10,000 is not so much. It's probably feasible. So I arrived at the end, and this, I hope, is what I convinced you of, so that by now crystal graph attentional networks can predict properties accurately. I would like to recall that this is not only because of the topology of the network and the 62 million parameters, it's also because of the large amount of data we have. And we can use them to discover new materials from unrelaxed structures. Now, we still have some challenges that are sometimes ignored in the literature. Our data sets are biased. All our data sets are biased. In the end, they all come from experiments, and they all come from published data, and there is a large human bias in these data sets that we haven't been able to get completely rid of. We have been able to mitigate it to some extent, but not completely get rid of. Then we have the challenge of the accuracy of the PB. I already gave you some hints on how we can go further in a computationally efficient way. And what we are currently working on is to finish exploring the chemical space of all known prototypes to get a real view of the large majority of materials that can be produced in the lab. This is possible in the next couple of years. To explore all properties that can be calculated. Any property that can be calculated can be machine learned in this way, and using transfer learning techniques, sometimes in a very efficient way. Then we are starting to look at thermal properties and temperature phase diagrams using universal force fields. We are getting close to the situation where the universal force fields have enough precision to be used to do this kind of calculations. And second, we started looking at high pressure phase diagrams. That's a natural evolution, and it's just a computational challenge by now. It's no longer a technical challenge. All the workflows are ready, all the methodology is there. It's just a matter of computational time, nothing else. I would like to thank you for your attention, and everybody that helped in this work. So my group in Halle still, we are, as I told you, we are in the process of moving to Bochum. Then my collaborators in Coimbra, with whom I did a lot of work, especially on superconductivity. Also Antonio Sana in Halle in the Max Planck, that has been a collaborator, a long-term collaborator in the superconductivity part, and Silvana Botti in Jena, that has been involved in most of the things I showed you. And thank you for your attention.